University of Ibadan ODE Integration Bee finals in the hardest problem 7. Okay, University of Ibadan is basically a university in Nigeria, and yeah, it's one of the world's popular university, and they have this ODE integration Bee every year. And yeah, and this is an integral which seems to be quite tough, right? Integral from 0 to infinity of cos of x by pi minus e by x squared dx, right? And I also gave this integral to Wolfram alpha to see if it can solve. Because Wolfram alpha is one of the most powerful calculator right now on the internet. And yeah, it just gave me a numerical answer and not an like analytic answer in terms of different constants, right? Okay, so yeah, we are going to solve this problem and it's gonna be a miracle. Okay, so first of all, like let me just tell that this pi and e don't will not really like mess up the solution. They're not really anything that will make the problem difficult. They're just there, and yeah, it will be quite easy actually. It will not be that hard. Okay, so and also notice that in this problem, uh, the cos is not squared, just the argument is squared, or just this x by pi minus e by x, this is only squared. Okay, now you might think like about how to simplify this, right? So for this one, like there's a theorem known as Glasser's-Master's theorem. Glasser's-Master theorem. This will like simplify the problem a lot. Now what this problem says is, let's say I have expression u in the form x, as don't get afraid, it is not that hard. X minus a, and then sum from let's say I from n to capital N, basically just some two different numbers, right? And I have this expression, some positive number divided by x minus any number b of n. This a n, b n, all of them basically are just some real numbers. Okay, now if I have such u and I have integral from minus infinity to infinity of f of u dx, the Glasser's master theorem says that this will just be equal to minus infinity to infinity of f of x dx, and this is a lot helpful. If I ever have any such expression, x minus a minus and then sum of different, I mean, you can just take it from I is equals to 1 to 2. If you just have two other rational fractions as u, right, you can just take any numbers. So I have some rational fractions of the form positive number divided by x minus b of n, then that will just be equal. And most of the time people just write a principal value over here, right? This is just to make sure that integral is defined even when there might be some singularities or some infinite limits, right? Basically, like if you write principal value, the thing that will be helpful is, let's say you have integral from a to b, let's say f of x dx, and let's say there is a singularity at point c, which is in between a and b, right? In between there's c, where f of c is basically just blast to infinity or something like that, right? So in that case, if you just write principal value, like this integral will be defined as integral from a to like c minus some epsilon, like very like slightly smaller value than c, f of x dx plus c plus epsilon to be fx dx. So yeah, principal value will basically define this integral in this way. So in this way, now there's no like such doubts, right? Now the singularity would not be a problem. So yeah, principal value will just help simplify the problem. So that's why we write it. Like even in the cases, let's say if we have this integral from minus infinity to infinity, writing principal value actually just gives sense to this integral. If you just write, so now this integral will basically mean that limit a goes to infinity from minus a to a f of x dx. So yeah, principal value is just a way of assigning a value to an integral which might seem to be improper or seem to have singularity at some point. That's the benefit of writing principal value. But yeah, we understand it without the principal value. Now let me just rub these things. We don't need this for now. I was just trying to show you what principal value actually is. Yeah, it's just a way so that we can assign values to integral even though they might seem to have singularity at some point in between or something like that. Over here also the fact is 8x is equals to bn, this integral might blast, right? 8x equals to bn. But even then, we can just break it into two integrals and then get a value. So yeah, so that's why we wrote principal value over here. Now, let us go on solving this integral using the Glasser's master theorem. So now, if we know this, like it will be a lot easier now. We'll just try to convert this x by pi into x, and then remaining things in the same form. We'll just try to get this integral in the same form so that we will be able to use Glasser's master theorem, right? So let me just say that y is equals to, okay, let me write the integral once again. So now we want this integral from 0 to infinity cos of x by pi minus e by x squared dx. Let me just write y is equals to x by pi. Then this integral will again still go from 0 to infinity, right? Because now 0 by pi is just 0, infinity by pi is just infinity. Now cos, and now this will just be y minus e by x is y pi, and then square. Now dx is just pi dy, right? Okay. Now this will just be pi integral from 0 to infinity cos of y minus e by y pi squared dy, right? Now to use Glasser's theorem, I need a u of the form x minus a minus some positive number, let's say a1 by x minus b1, again a2 by x minus b2, of this form, right? And it goes on. Okay, so over here also I can definitely have the same form. You can just say that if I just write it in this form, let's say I write it as pi integral from 0 to infinity cos of u minus, I can just have a as 0, right? Doesn't matter. Yeah, you understand that. Minus, this is just e by pi by y minus 0 again. And others are just 0, right? So it goes in dy. Now, definitely, the only condition is this number should be positive, minus, and then there should be a positive number. So our e by pi is definitely a positive number. And yeah, the rest of the condition, this b1, b2, they can be any real number. So yeah, it doesn't matter if they are 0. It can be any real number, doesn't matter it's 0. It here need to be x, so we definitely have just y over there. So yeah, so this is now in the form that we need to use Glasser's master theorem, right? So yeah, this integral now will just be equal to, using the Glasser's master theorem, pi integral from 0 to infinity cos of, oh, I forgot a square over here. Now this will just be y square dy, right? Okay, now guys, you might have already seen this integral cos of y square dy. This is a really famous integral actually. No, not this one, I mean this one. Minus infinity to infinity of cos of x squared dx. This is a really famous integral, and this is known as the Fresnel integral. And this is a really popular one. You can find like hundreds of solutions on the YouTube, and this is actually equal to square root of root pi by 2. I will definitely give one proof in this video. Like most of the proof in the YouTube are based on complex analysis, but my proof will basically be without the complex analysis. Yeah, definitely easier than those on the YouTube. Okay. So yeah, now we are going to, now if you just know the Fresnel integral. So first of all, I can write it as, since this cos of y square, this is just even function, right? Because there's y square in there. So yeah, I can definitely write it as pi by 2 times, now from minus infinity to infinity, cos of y square dy. I just extended the domain because that was even function. And yeah, I just introduced pi by 2 because its value from minus infinity to 0 and 0 to infinity, they are going to be same. So if I just halve it, I'm going to get value from 0 to infinity. So now we know that this is the Fresnel integral. We will definitely give a proof after I write the answer. So yeah, you can wait for that. This is pi by 2 times, we know that now it's a Fresnel integral, so this is just root pi by 2. And the answer is pi by 2 to the power 3 by 2. If you find the answer will be exactly the same as all prime alpha gave me, 1.9687, right? But we now also have the analytic form that it's just pi by 2 to the power 3 by 2. And yeah, so see, sometimes we are humans, we can definitely better than these algorithmic stuff than these robots, right? Okay. So now with that being said, now let's try to prove the Fresnel integral. Proof of Fresnel integral. Proof of. And you just see that even though this problem might have seemed hard, using the Glasser's master theorem made it too easy, right? Proof of Fresnel integral. Okay, we want to show that integral from minus infinity to infinity of cos of x squared dx is equals to root pi by 2, right? And also, even if there's sine of x squared dx, the answer will be same. Those two are actually equal, right? Okay. Also, you might want to see why those two are equal. You can definitely go to YouTube, but for now, let's just prove this. So I'm going to prove this using Laplace transform, right? Using Laplace transform. Right? Now, if you don't know what Laplace transform, you might still be able to understand. I don't know. You can just try to follow. Laplace transform of a function is just defined as, this is just L, is defined as, like, let's say I want to transform this function f of t to the world of s using Laplace transform. This is just defined as integral from 0 to infinity of e to the power minus st f of t dt. So yeah, wait, this space is not enough. I guess you understand it, right? Okay, dt. Now, in this case, we have this integral from minus infinity to infinity of cos of x squared dx, right? And we know that this is just twice of the integral from 0 to infinity of cos of x squared dx, right? First of all, I will make a definition. I will define another function. Let's say I of t, which is integral from 0 to infinity of cos of tx squared dx. I'll basically try to solve for this integral, and then later on, if I substitute t as 1, I will get this required integral, right? Okay, so let me solve this one. To solve this one, I said that I'm going to use Laplace transform. So let me just take the Laplace transform of this integral, right? And that will just be integral from 0 to infinity of e to the power minus st. And then integral. This integral will basically give an answer in terms of t, right? Because this integral is in terms of dx, so dx will just get simplified, but t will still be there, so the answer will be in terms of t. And yeah, I'm going to take the Laplace transform of this I of t and change it to the world of s. Okay, yeah. So yeah, I want to take integral in terms of t, so basically this s variable will just remain. So yeah, the answer will be in terms of the s variable. Now we know that I of t is just integral from 0 to infinity of cos of tx squared dx, right? And this dt will just be as it is. Now notice that this integral is in the world of x, this inside integral is in the world of x, right? So that's why I can just take the e to the power minus st inside that integral. 0 to infinity, 0 to infinity. It's just a constant for that integral, right? E to the power minus st cos of tx square dx dt. Now, since like both of these integrals are just like the domain of these integrals is just constant, right, from 0 to infinity, 0 to infinity, I can just switch them up if they are just constants, right, without making any changes. Definitely, I need to switch dx dt to dt dx, but yeah, I can do that. 0 to infinity, 0 to infinity. There are some convergence issues which you might take upon yourself that we don't have any problem with them. We don't really have any problem about the convergence. You can take that upon yourself. Let me just assume and go. Now we need to solve. We want to solve this, right? Now, notice that the inside integral, this one, is a Laplace transform that we know. This one is a Laplace transform that we know. This one is just for, okay. Now for this integral in terms of t, x square is just constant, right? I mean for the integral in terms of t. So this is just the same as integral from 0 to infinity e to the power minus st cos of at dt, which is just a Laplace transform of cos of at. And we know that the Laplace transform of cos of at in the world of s is just s by s square plus a square. So if we use this result, this will just be integral from 0 to infinity of s by s square plus a square, right? And now this is a pretty simple integral. Please don't forget that this is actually a Laplace transform of I of t to the world of s. Okay, let me just remind you if in case you forgot that. 0 to infinity s by s square plus x to the power 4 dx. Now this one over here is just a simple application of the famous beta gamma function, right? You can actually solve this easily using the beta function. This definition of beta function, that beta of xy is just equals to integral from 0 to infinity of t to the power x minus 1 by 1 plus t to the power x plus y dt. You can use this definition of beta function to solve this. So I just need to make this as 1 and this as just a t, and yeah, this will be solved. And also let me tell you that beta of xy is defined as gamma x gamma y by gamma of x plus y. These are just some like techniques of the old times, I mean of the past, right? These days most of the time we just use complex analysis and we don't need to use any of such old things. Like integrals get easily solved, but still I'm just trying to be like the Euler or let's say Laplace people of those times. Okay, yeah, that is just a joke. Now let's just try to solve this one. First of all, I want to make this s square as 1. So for that, I can just take, let's say, s common from numerator, s square common from denominator, right? 1 to infinity 1 by, this is just 1 plus x to the power 4 by s square. And this is just dx, right? Now I need to make this as t. So I will just let it, I will just let that t is equals to x to the power 4 by s square. If I let that, okay, if I let that, now we know that x to the power 4 is just ts square and x is just t to the power 1 by 4 s to the power 1 by 2 dx is just s to the power 1 by 2 times 1 by 4 t to the power minus 3 by 4 dt, right? So this will be equal to 1 by s integral from 0 to infinity 1 by 1 plus t, right? And now the dx is just s to the power 1 by 2 1 by 4 t to the power minus 3 by 4 dt, right? Now I can take the constants out, so s to the power 1 by 2 by s to the power 1 by 4. And again, still know that this is still a Laplace transform of I of t to the world of s, right? Don't forget that. That will be important to find the IFT later on. And now this will just be integral from 0 to infinity of t to the power minus 3 by 4 by 1 plus t dt. Now this is in a good form to use beta function. Note that in numerator we need to have power x minus 1. Over here we need to have power x plus y, right? So this will be equals to 1 by this is not 1 by 4 in denominator. In denominator, I'm sorry for that. This is just 4. That's just 4. Right? Okay. And now this is just 4 root s. 4 root s. And now this is, I'm right, guys, right? I don't think I've messed up. Okay. Now I need to write that as x minus 1 over here. So 1 by 4 minus 1. I need to write it as x plus y. And x is 1 by 4 already. And I know that this power is initially just 1, so I need to write plus 3 by 4, right? Okay, now I know I have the value of x as 1 by 4, y as 3 by 4. So this will just be 1 by 4 root s beta of 1 by 4 comma 3 by 4. Now beta of 1 by 4 comma 3 by 4 is just defined as gamma 1 by 4 gamma 3 by 4 divided by gamma of 1 by 4 plus 3 by 4, right? Now gamma of 1 by 4 plus 3 by 4, that's just Gamma of 1, right? That's just gamma of 1, right? We know that gamma of 1 is just 1. And for the numerator, we will use this formula that gamma of n, gamma of 1 by n is pi by sine of n pi, which is just a reflection formula of gamma function. So this will be 1 by 4 root s. That will just be pi by sine pi by 4 divided by 1. So this will be pi by 4 root s. Sine pi by 4 is 1 by root 2. So this will be pi by root s times 2 root 2. So basically pi by 2 root 2 times 1 by root s. This is our Laplace transform of the integral to the world of s. Now to find the I of t, we need to just take the Laplace inverse, just take this Laplace to other side, it becomes Laplace inverse, right? And again, like Laplace inverse of constant times some function is equals to just, I can take the constant out, so this will just be pi by 2 root 2 times Laplace inverse of 1 by root s, right? Now if you are to find Laplace inverse, you just need to know the Laplace of which function gives this one, right? Now there's root s. Now if you just analyze, let's say if you take Laplace of t to the power minus 1 by 2, this will just be 0 to infinity e to the power minus st t to the power uh, minus 1 by 2 dt. If you do this, we know that this one is just gamma of 1 by 2 by s to the power 1 by 2, right? This minus half power will just be increased by 1. Now you see that if I take Laplace of the t to the power minus 1 by 2, I exactly have the root s in denominator, right? So normally if you just have s to the power 3, you would have taken t square, because you know that it just increased by 1. So that's actually a pattern over here, and you can understand that. Now, okay, now if you wanna find just s to the power 1, but now if you wanna just take Laplace inverse, take this Laplace to other side, and gamma 1 by 2 is just a constant. You can take that out of Laplace. So this is Laplace inverse of, my Laplace inverse symbol is becoming more and more like set symbol, I'm sorry. Okay, so Laplace inverse of 1 by square root of s. So now we have Laplace inverse of 1 by square root s, right? And I guess you guys know that gamma of 1 by 2 is just root pi. So this is just t to the power minus 1 by 2 by root pi is Laplace inverse of 1 by root s. Okay, so now we know that Laplace inverse of 1 by root s is just pi by 2 root 2. Now this is just t to the power minus 1 by 2 by root pi. So our I of t just becomes root pi by 2 root 2 times t to the power minus 1 by 2. Now our I of t was integral from 0 to infinity of, wait, there's no enough space. Wait, let me just write somewhere else. Now our this I of t is just equals to integral from 0 to infinity. There's still no enough space, I'm sorry. Now we know that this I of t was just integral from 0 to infinity of cos of tx squared dx, right? And now when you see that this is equals to root pi by 2 root 2 t to the power minus 1 by 2, right? Now if we just substitute t is equals to 1, we will get the required integral, that cos of x squared dx is just root pi by 2 root 2. Now if I make the domain of integration from minus infinity to infinity, since it's just an even function, this one will just be twice the original integral, right? This integral from 0 to infinity of cos of x squared dx. We know that this is just root pi by 2 root 2. So this our intended Fresnel integral is just root pi by root 2, which is exactly in the form that root of pi by 2. And that's how we solve the Fresnel integral, guys. So we have solved the Fresnel integral, and that means, yeah, we have now definitely solved our original problem, because we are stuck over here in the Fresnel integral. I just told you that there are proofs on YouTube, but now we did prove it. So yeah, definitely this problem might have like seemed to be hard problem in the beginning, but after we just use the Glasser's master theorem, we found out that this is actually just a Fresnel integral whose value is just root under pi by 2. And to find the Fresnel integral, we just first took the define it as I of t as integral from 0 to infinity of cos of tx square, and then took the Laplace transform, and then after Laplace transform we found out that we already knew the Laplace transform. And this is also not, you might have seen that I just used this result. This is again not that hard to prove. You can just use the fact that cos of t is actually a real part of e to the power it, and then you can just use the Laplace transform e to the power it, which can be easily evaluated from the integral definition itself. You can get this result. So after that, we just transform it to beta gamma function, which are just some old school techniques of evaluating integrals in this world, where everyone just uses complex analysis because that's more easier. And after that, using beta gamma function, we solve this problem, right? If you use beta gamma function, you just feel like you are once again going to those 18th century. But yeah, that's fine if you want, if it's helpful, right? And yeah, we solved it. So that was it. Hope you enjoyed the video. Thanks for watching. And for such interesting problems, be in touch with us. Thanks for watching.